welcome to this problem walkthrough. Today, we're tackling problem number 1351, count negative numbers in a sorted matrix. In this problem, we'll explore how to efficiently count the number of negative numbers in a matrix where rows and columns are sorted. Let's dive in. In this problem, we are tasked with counting the number of negative numbers in a matrix that is sorted in a specific way. The matrix, which we refer to as grid, has dimensions m by n, meaning it has m rows and n columns. The key detail here is that the matrix is sorted in non-increasing order both row-wise and column-wise. This means that within each row, values decrease as we move from left to right, and within each column, values decrease as we move from top to bottom. The goal is to determine how many of the numbers in this matrix are negative. To achieve this, the input will be the matrix itself, represented as a 2D array, and the output will be a single integer that represents the total count of negative numbers found in the matrix. Let's look at an example to understand the problem better. Here, the input matrix is a 4x4 grid where each row and column is sorted in non-increasing order. The matrix is shown as 4, 3, 2, -1 in the first row, 3, 2, 1, -1 in the second, 1, 1, -1, -2 in the third, and -1, -1, -2, -3 in the fourth. When we examine the grid, we can see that the top left portion contains positive or zero values, while the bottom right portion contains the negative values. Counting these negatives, we find there are 8 in total, for occurrences of -1, 2 of -2, and 2 of -3. Therefore, the output for this example is 8. Now consider a simpler example where the input is a 2x2 matrix. The grid contains the numbers 3 and 2 in the first row, and 1 and 0 in the second row. Here, all the values are non-negative, so there are no negative numbers to count. As a result, the output for this example is 0. This demonstrates that the solution must handle cases where there are no negative numbers present in the matrix. For another example, this time the input is a 2x2 grid that includes negative numbers. The matrix is structured as follows: 1 and -1 in the first row, and -1 and -2 in the second row. Following the sorting constraints, we observe 3 negative numbers in total, 2 occurrences of -1 and 1 of -2. Counting these gives us the output of 3. This example highlights how the sorting of the matrix allows us to efficiently identify where the negative values are concentrated. To solve this problem, we need to consider the constraints provided. First, the number of rows in the matrix, m, is equal to the length of the grid, and the number of columns, n, matches the length of each row. Both m and n will range between 1 and 100. Additionally, the values in the matrix will fall between -10,000 and 10,000, and the sorting property applies to both rows and columns, ensuring a non-increasing order. These constraints ensure that the matrix is well defined and allows us to focus on an efficient strategy to count the negative numbers. Finally, let's consider some edge cases. If the matrix contains no negative numbers, such as in the example with input 1, 0, 0, -1, the output will be 1, as there's just one negative number. If the matrix is entirely negative, such as -1, -2, -3, -4, then every element contributes to the count, giving us an output of 4. For matrices with a single row or column, like 1, 0, -1, -2, the output is 2 because there are 2 negative values. And for matrices with mixed distributions, such as 4, 3, -1, -2, -3, -4, -5, -6, the output is 6. These examples illustrate the variety of scenarios your solution needs to handle effectively. To solve the problem of counting negative numbers in a sorted matrix, the brute force approach is the most straightforward. The intuition here is simple: we iterate through every single element in the matrix, one by one, and check whether it is negative. To achieve this, we loop through each row of the matrix, and within each row, loop through every column. If an element is negative, we increment our counter. While this approach is easy to understand and implement, it doesn't take advantage of the sorted nature of the matrix. It also has a time complexity of m*n, where m is the number of rows and n is the number of columns, making it inefficient for large matrices. On the other hand, it uses constant space, which is a positive aspect. However, for larger datasets, the inefficiency in computation outweighs the simplicity, making it less practical. A more efficient alternative is the binary search approach, which leverages the fact that each row in the matrix is sorted in decreasing order. The key observation here is that once we encounter a negative number in a row, all subsequent elements in that row will also be negative. Using binary search, we can quickly find the first negative numbers index in each row. The algorithm begins by initializing a counter to 0. For each row, we perform a binary search to locate the smallest index where the element is less than 0. The count of negative numbers in that row is simply the total number of elements in the row minus this index. Adding this to our total count gives us the desired result. This approach improves the time complexity to O, m asterisk log n, as binary searches apply to each of the m rows. Although it requires a slightly more complex implementation compared to brute force, it is significantly faster and utilizes the sorted property of the rows effectively. Another highly efficient method is the greedy traversal approach, which exploits the fact that the grid is sorted both row-wise and column-wise. By starting at the top right corner of the matrix, we can make decisions to either move left or down based on the value of the current element. If the current element is negative, we know that all elements below it in the same column are also negative, so we add those to the count and move left. If the current element is non-negative, we move down to the next row. This traversal ensures that each row and column is visited at most once, resulting in a time complexity of O, m plus n. The algorithm is simple to implement and highly efficient, though it may feel less intuitive initially. Overall, it is an excellent example of how understanding the structure of the problem can lead to an optimized solution. The key insight for solving this problem efficiently lies in recognizing the sorted structure of the matrix, specifically, that it is sorted in non-increasing order both row-wise and column-wise. This allows us to bypass unnecessary computations by strategically navigating the matrix. The aha moment here is realizing that starting from the top right corner enables a greedy traversal that minimizes redundant checks while counting negatives effectively. After evaluating the options, the greedy traversal approach stands out as the chosen strategy. It offers a time complexity of O, m plus n, which is optimal for large matrices, and its implementation is relatively straightforward. While the binary search approach is also efficient at O, m asterisk log n, it introduces additional complexity and doesn't perform as well when the dimensions of the matrix are comparable. The brute force method, though simple, is ruled out due to its inefficiency. By fully leveraging the grid's sorted properties, the greedy traversal method provides the best balance of simplicity, efficiency, and practicality for this problem. To solve the problem of counting negative numbers in a sorted matrix, we can start with a brute force approach. In this matrix, each row is sorted in non-decreasing order, and our goal is to count all the negative numbers. The first step is to initialize a counter variable called negative_count and set it to 0. This variable will track the total number of negative numbers as we process the matrix. Next, we use an outer loop to iterate through each row of the matrix. For each row, we extract its contents, and we keep track of the row index, I, which we'll use to access individual elements. Once we have the current row, we move to the next step of iterating through its columns using an inner loop. In this step, we process each element of the row by accessing it through its column index, j. This structure ensures that we systematically visit every element in the matrix. At this stage, we focus on checking if each element in the matrix is negative. For every element matrix I, j, we perform a simple comparison to see if the value is less than 0. If the condition is true, we increment our negative_count variable by 1. This ensures that we capture all the negative numbers as we traverse the matrix. The inner loop continues until all columns in the current row have been processed, and then the outer loop progresses to the next row. This process is repeated until all rows and columns in the matrix have been examined. Once every element has been checked, we return the value of negative_count. This value represents the total count of negative numbers in the matrix and serves as our final result. Now let's reflect on some key insights about this brute force approach. First, it processes each element of the matrix individually, meaning it does not take advantage of the fact that the rows are sorted. As a result, it performs unnecessary checks even when they could be avoided. In terms of time complexity, this approach iterates through all m*n elements in the matrix, leading to a time complexity of O, m*n. On the other hand, the space complexity is very efficient, as the algorithm does not require any additional data structures. Apart from the input matrix, the only extra variable used is _count, making the space complexity 1. These characteristics highlight the simplicity of this approach, but also its inefficiency for larger datasets. It's important to consider edge cases when designing an algorithm. For instance, if the matrix is empty, there are no rows or columns to process, so the function should immediately return 0. If the matrix contains only positive numbers, the algorithm should correctly return 0 as well, since no negative numbers are present. In the case where all the numbers in the matrix are negative, the count should equal the total number of elements, which is m*n. Finally, the algorithm should handle matrices with a mix of positive, negative, and 0 values seamlessly, ensuring that only the negative numbers are counted. The input itself is a 2D list or array of integers, with each row sorted in non-decreasing order. The only additional data structure used is the counter variable _count, which tracks the total count of negatives during the iteration. Let's break down the key operations involved in this brute force approach. First, accessing an element in the matrix I, j, is a constant time operation, 1. This is because the matrix is stored as a 2D array, allowing us to directly retrieve elements using their indices. Next, the negativity check, where we compare matrix I, j, with 0, is also a simple comparison and takes constant time, 1. Finally, when we increment the _count variable, this operation is likewise performed in 1 time. These constant time operations are repeatedly performed for each element in the matrix as we iterate through rows and columns, contributing to the overall time complexity of the algorithm. To better understand how the algorithm works, let's walk through an example. Consider the input matrix, -3, -2, -1, 1, -2, 2, 3, 4, 4, 5, 7, 8. We start by initializing _count to 0. In the first row, -3, -2, -1, 1, we check each element. -3 is less than 0, so we increment _count to 1. -2 is also less than 0, so we increment it again to 2. -1 is negative as well, bringing the count to 3. The last element, 1, is positive, so we do nothing. Moving to the second row, -2, 2, 3, 4, we start with -2, which is negative, so we increment _count to 4. The remaining elements, 2, 3, and 4, are positive, so no further increments are made. Finally, in the third row, 4, 5, 7, 8, all the elements are positive, so there's nothing to count. At the end of the iteration, the _count remains 4. This is the total number of negative numbers in the matrix, so we return this value as our output. While this brute force approach is straightforward and ensures correctness, it doesn't utilize the sorted property of the matrix. Optimized algorithms, such as those that use binary search or reverse traversal, can significantly reduce the time complexity to m+n, or m*log n, making them more efficient for larger matrices. These methods avoid redundant checks and take advantage of the structure of the data to achieve faster results. The provided Python implementation solves the problem of counting the number of negative numbers in a sorted matrix efficiently using binary search. Here is a detailed explanation of the code. 1. Initialize the counter asterisk. The variable _count is initialized to 0 at the beginning of the count negatives function. This variable will store the total count of negative numbers found in the matrix. 2. Iterate over the rows asterisk. The for loop iterates through each row in the grid. Since each row is sorted in non-decreasing order, binary search can be applied to locate the first negative number efficiently. 3. Binary search per row asterisk. For each row, variables left and right are initialized to the start and end indices of the row. A while loop is used to perform binary search. The midpoint mid is calculated as left plus right, //2. If the element at mid is negative, it means all elements to the right of mid, including mid, are also negative due to the sorted property. Hence, the search range is updated to the left part of the row by setting right equals mid 1. If the element at mid is non-negative, the search range is updated to the right part of the row by setting left equals mid plus 1. 4. Count the negatives in row asterisk. Once the binary search is complete, left points to the index of the first negative number in the row, if any. All elements from this index to the end of the row are negative. The count of negative numbers in the row is calculated as len, row, left and added to negative underscore count. 5. Return the result asterisk after processing all rows. The total count of negative numbers in the grid is stored in negative underscore count, which is returned as the result. ### complexity analysis. Time complexity asterisk. Each row is processed using binary search, which runs in O log n time for a row of length n. If there are m rows, the overall complexity is O m asterisk log n, where m is the number of rows and n is the number of columns. Space complexity asterisk. The algorithm uses O1 additional space as no extra data structures are used. This implementation is efficient and takes advantage of the sorted structure of the matrix, making it suitable for large inputs. This is the Java implementation for LeetCode problem number 1351, count negative numbers in a sorted matrix. The solution mirrors the Python logic using Java constructs. It iterates through each row of the matrix and applies binary search to find the first negative number in the row. The count of negative numbers in the row is then added to the total. Key differences include the use of Java syntax, type declarations, and enhanced for loops for iterating through the rows. To solve this problem, we start by initializing a variable called negative underscore count to 0. This will help us keep track of the total number of negative numbers in the grid. Now, for the first row, which is 4, 3, 2, -1, we perform a binary search to locate the first negative number. Initially, left is set to 0, and right is set to 3. At mid equals 1, the value is 3, which is non-negative, so we move the left pointer to mid plus 1, which is 2. Next, at mid equals 2, the value is 2, so again, we move left to mid plus 1, making it 3. Finally, at mid equals 3, the value is -1, which is negative. This time, we move the right pointer to mid 1, which becomes 2. Now, the left pointer points to index 3, meaning all elements from index 3 to the end are negative. We calculate the count of negatives in this row as len, row, left, which is 1, and add it to negative underscore count, updating the total to 1. For the second row, 3, 2, 1, -1, we repeat the binary search. At mid equals 1, the value is 2, so we move left to mid plus 1, which is 2. At mid equals 2, the value is 1, so left is increment to 3. At mid equals 3, the value is -1, so we move right to mid 1, which is 2. Again, left points to index 3, and the count of negatives is 1. Adding this to our total, negative underscore count becomes 2. Now, let's analyze the third row, 1, 1, -1, -2. In the third row, 1, 1, -1, -2, we begin the binary search with left equals 0 and right equals 3. At mid equals 1, the value is 1, so it's non-negative, and we move left to mid plus 1, which is 2. At mid equals 2, the value is -1, so it's negative, and we move right to mid 1, which is 1. Now, left points to index 2, meaning all elements from index 2 to the end are negative. The count of negatives in this row is len, row, left, which equals 2. Adding this to our total, negative underscore count becomes 4. Finally, for the fourth row, -1, -1, -2, -3, we perform the binary search again. With left equals 0 and right equals 3, at mid equals 1, the value is -1, so it's negative, and we move right to mid 1, which becomes 0. At mid equals 0, the value is still -1, so we move right to mid 1, which is -1. At this point, the left pointer is at index 0, meaning all elements in the row are negative. The count of negatives in this row is len, row, left, which is 4. Adding this to our total, negative underscore count becomes 8. The final output for this example is 8. In this example, the grid is smaller, containing only 2 rows, 3, 2, and 1, 0. We initialize negative underscore count to 0. For the first row, 3, 2, we perform a binary search. With left equals 0 and right equals 1, at mid equals 0, the value is 3, which is non-negative, so we move left to mid plus 1, which is 1. At mid equals 1, the value is 2, so again, we move left to mid plus 1, making it 2. At this point, left is equal to the length of the row, meaning there are no negative numbers in this row. The count of negatives is 0, so negative underscore count remains 0. For the second row, 1, 0, we repeat the binary search. Starting with left equals 0 and right equals 1, at mid equals 0, the value is 1, which is non-negative, so we move left to mid plus 1, which is 1. At mid equals 1, the value is 0, so again, we move left to mid plus 1, making it 2. Again, left is equal to the length of the row, so there are no negative numbers in this row either. The count of negatives is 0, and negative underscore count remains 0. The final output for this example is 0. For this final example, the grid contains only one row, -1. We initialize negative underscore count to 0 and perform a binary search on the single row. With left equals 0 and right equals 0, at mid equals 0, the value is -1, which is negative, so we move right to mid 1, which becomes -1. At this point, the left pointer is at index 0, meaning all elements in the row are negative. The count of negatives is len, row, left, which equals 1. We add this to negative underscore count, resulting in a total of 1. Since this is the only row in the grid, the final output for this example is 1. Here, we analyze the time complexity of our solution. The algorithm begins by iterating through each row of the matrix, and since there are m rows, this contributes m to the overall complexity. Within each row, we apply binary search to locate the first negative number. Binary search is highly efficient, operating in log n time for a row within columns. Since binary search is repeated for every row, this step adds up to m asterisk log n for the entire grid. After locating the first negative number in a row, the count of negatives is simply the difference between the row length and the index of the first negative number. This calculation is a constant time operation, 1, for each row. When we combine these steps, the total time complexity becomes m for the row iteration, plus m asterisk log n for binary searches, and m asterisk 1 for the constant time calculations. Together, these simplify to m asterisk log n. The final expression for time complexity is m plus m asterisk log n plus m asterisk 1, which simplifies to m asterisk log n. Now, let's consider the space complexity. The algorithm uses a few auxiliary variables, such as negative underscore count, left, right, and mid, for calculations during the binary search. These variables require constant space, 1. The input matrix itself takes up m asterisk n space, but since it's provided as input and not additional memory allocated by the algorithm, it doesn't contribute to the space complexity. Importantly, the solution avoids using extra data structures or recursive calls. Therefore, the overall space complexity of this solution is 1. When we compare this solution to a brute force approach, we can see significant improvements in efficiency. The brute force method involves iterating through every cell in the matrix to count the negative numbers. This approach has a time complexity of m asterisk n, as every cell in the mxn matrix is explicitly checked. However, it uses no additional space, giving it a space complexity of 1. In contrast, the optimized solution leverages binary search on each row, which reduces the time complexity to m asterisk log n. Like the brute force method, it also uses no additional space, maintaining an 1 space complexity. This comparison highlights how binary search drastically reduces the time required to process large matrices while keeping memory usage minimal. Now, let's analyze the best, average, and worst-case scenarios for this solution. In the best case, all rows contain only positive numbers. Binary search terminates quickly, often after just 1 or 2 iterations per row. However, this does not impact the overall time complexity, which remains m asterisk log n. In the average case, the rows contain a mix of positive and negative numbers. Binary search will perform its usual log n operations for each row, leading to an overall complexity of m asterisk log n. In the worst case, most elements in each row are negative, meaning binary search runs for the full log n iterations on every row. Despite this, the total time complexity remains m asterisk log n. Thus, regardless of the input distribution, the algorithm maintains this asymptotic efficiency. To solidify our understanding, let's examine the mathematical reasoning behind the m asterisk log n time complexity. Binary search works by having the search space in each iteration. Starting with n elements, the search space reduces to n/2, then n/4, and so on, until only one element remains. This process completes in log n iterations. Since we perform binary search on each of the m rows, the total number of operations scales as O, m * log n. As for space complexity, the algorithm simply uses a few variables for computations, all of which require constant space. No additional memory is allocated, giving us a space complexity of O(1). This analysis confirms the efficiency of the solution both in terms of time and space. A common pitfall in matrix problems is failing to utilize the properties of sorted rows or columns. These properties often allow for optimized solutions, but if overlooked, you might resort to slower methods like brute force. Another frequent mistake involves boundary conditions. When working with a 2D grid, it's easy to miss edge cases, such as skipping the last row or column or accidentally accessing indices outside the matrix bounds. Additionally, assuming all inputs are valid can trip you up. For example, you might encounter edge cases like empty matrices or grids with only one row or column. Lastly, misunderstanding problem constraints is another area where errors occur. For instance, overestimating input sizes might lead to unnecessarily complex solutions. If the matrix is too large to fit into memory, consider alternatives like row-by-row traversal to process the data efficiently. Directly using nested loops with O, m * n complexity, when more efficient techniques like binary search are viable, can lead to performance issues like time limit exceeded errors. Instead, focus on identifying patterns or properties in the matrix, such as sorted rows or diagonal relationships, as these can simplify the solution significantly. During interviews, always ask questions to clarify constraints and properties, which can guide your approach. Space complexity is another key consideration. Aim to minimize space usage unless the problem explicitly requires additional memory. For example, in-place modifications or avoiding redundant data storage can be advantageous. Don't forget to verify your solution with edge cases like empty matrices, single-element grids, or matrices where all numbers are either entirely positive or negative. And remember, if rows or columns are sorted, binary search can be a powerful tool to optimize your solution, often reducing complexity to O, m * log n, or even O, log m * n in certain cases. There are several related problems that build on similar concepts. Problem 74, search a 2D matrix, involves a matrix where rows and columns are sorted, and the solution uses binary search to efficiently locate a target value. Problem 240, search a 2D matrix 2, also deals with a sorted matrix, but it introduces diagonal traversal as part of the strategy. Of course, the problem we're discussing, count negative numbers in a sorted matrix, is another example that leverages the sorted properties of the matrix to count elements efficiently. Lastly, problem 378, kth smallest element in a sorted matrix, focuses on extracting specific elements from a sorted matrix, again using its properties to optimize the solution. These problems highlight how recognizing the inherent structure of the data can streamline your approach. There are multiple approaches to solving matrix problems, each with its own trade-offs. Brute force, for example, involves iterating through every element, with a time complexity of O, m * n, and space complexity of O(1). While simple to implement, it's inefficient for larger matrices. Binary search offers a more optimal solution when rows or columns are sorted, reducing time complexity to O, m * log n, or even O, log m * n, under certain conditions, while maintaining a space complexity of O(1). However, it requires a solid understanding of binary search logic to implement correctly. Another efficient method is greedy traversal, such as starting from the top right corner and moving strategically based on the matrix's sorted properties. This approach has a time complexity of O, m + n, and space complexity of O(1), making it ideal for problems like counting specific values. While efficient, it may take additional effort to design the traversal logic and ensure correctness. Great job reaching the end of this problem. To summarize, we explored different ways to count negatives in a sorted matrix, highlighting both brute force and optimized solutions. Remember to leverage sorting properties when tackling similar problems. If you enjoyed this video, like, share, and subscribe for more problem walkthroughs. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!